estimate the parameters of the model. Now, each one of those things is obviously a complicated situation, and so you're going to have to provide information to the Dynare. And the information that's provided is provided in a program. Let's call it ProgMod. The key thing being MOD. MOD is a file with an extension MOD that has in it instructions about what you want to do. Solve, simulate, or estimate. And so this file is going to have a bunch of stuff in it. So one obvious thing you're going to need in any case is you're going to have to provide the model. You have to communicate what the model is to this thing. And so there's a syntax in Dynare that we'll get to for telling it what the model is. And then you're going to have to give it instructions about what to do with the model. So you'll have to tell it, do you want to only solve it and then stop? Do you want to simulate it? Well, if you want to simulate it, you're going to have to tell it, exactly in response to what do you want to simulate it. If you want to estimate it, of course, then it's going to go wild in terms of how much information you need to provide. You need to tell it where's your data, what data set is it, what's the first observation you're supposed to use in your data set, what's the last observation, should you remove the trends from the data first, or whatever, all kinds of little details that you have to tell it. Then, of course, it'll do Bayesian estimation, which means, you have to tell it what your priors are, what are the parameter values of your prior. You have to provide all the information that you would think that you have to provide. You have to write this all into this file. And then what Dynare does, it's a program that you execute from inside MATLAB. And what Dynare does is Dynare takes the prog file, prog.mod. You made up this name here, and it's going to produce, it produces a bunch of MATLAB files. That is, M files. Dynare is something you execute from inside MATLAB. You feed it your mod file. It eats the mod file, and then it translates the mod file, what it ate in there, into MATLAB instructions, which are then able to implement whatever it is that you want to do. That's the basic idea about Dynare. It's a little bit like, I don't know, of course nobody here knows about this, but like Fortran, for example. Fortran has its own personal language, and you would put it into a special Fortran file, and then Fortran would eat the file and translate it into machine language and then execute. And Dynare, it's kind of like that, although at a higher level, because Dynare is a higher level even than MATLAB, and MATLAB is already a pretty simple thing. Okay, so let's get more into the situation here with Dynare. So that we need to locate the files. And so what that means is that the CGG thing has very little in it, actually. It's a very, very simple little, it looks like it has nothing. No, wait. Whatever. Huh? Wait, I hear people saying things, but... No. This is supposed to work. But it's also a zip file, so I'm not... Anyway, whatever. If we look at that zip file, we should find it. Gunk, if you do that. But the thing is, you guys, you have to take the code out of the zip file and copy it into normal space. Oh, you already did it. Okay, great. All right, so now here we have the program, and it's a amazingly simple little job here. And so what I want to do is talk a little bit about the. No, I can't see that either myself. It's like it's nothing there. Talk about the syntax of this thing. So I mean, we could jump directly to here. This model command has by the way, these commands, they have the property they follow by an end. When the command is over, it's got an end. And you have to have semicolons after everything. Otherwise, it runs, it doesn't recognize blanks. So if you don't have a semicolon, it just thinks whatever comes next is part of that particular command. So the first thing is model, and the last thing here is end, and then you type in your model, not surprisingly. And this has already been linearized. Normally you would write in the nonlinear equations, and it would linearize it for you. Now we're writing in the linear equations, and we're also giving a little bit of an assist by telling them that they're linear. Of course, if we didn't tell them it was linear, it would just linearize it, and well, then they would still be linear. So you're just saving it a little bit of the electrons that have less running around to do if you type in linear here. As I say, I'm pretty sure that Jesus will have an example with the RBC model, and then you'll have the nonlinear equations in there too. Also, by the way, my website is just littered with these types of zip files with all kinds of examples, including RBC and stuff like that. Anyway, here's the pricing equation. And now notice that when you look at these equations, you start to see there's kind of different types of variables. So the two types of, there are really three types of variables in Dynare, but there's like two really fundamentally distinct variables. One is like a constant, and the other one is a time series variable. Thank you. Yeah. Yeah, that's great. Thank you. So one is a constant. And so if we look at this beta, of course, this ain't no time series variable. This is a constant here. But the pi guy is a time series variable. Now, in order for it to know this, pi is inflation, of course, you have to declare this stuff in advance. So let's go back and see how those declarations are made. If we go to the first line here, well, I got two slashes there. That's a comment. So Dynare totally ignores that line. The line here says var, and in the var command is where you declare what are your time series variables. There's a variable called da. Da is the change in A. And then there's inflation, and there's R, the net interest rate. Then there's the net natural interest rate. There's tau, which is the backache thing. That's the preference shock and the utility function. U is a monetary policy shock. And X is the output gap. In here. Now, then here are the parameters. Parameters are constants. Phi, beta, kappa. This is the coefficient on X in the policy rule. This is the slope of this is all the same notation that I had in the handout. Phi pi is the weight on inflation. Alpha is the smoothing parameter in the policy rule. Rho is the autoregressive parameter of the technology growth rate. And lambda is the coefficient on back pain, and delta is the autoregressive coefficient on the monetary policy shock. These are all parameters. You don't actually have to put all the parameters into the parameter statement, but if there are any parameters that, see what Dynare does is to repeat this thing here. So it takes your, what is it? I called it ProgMod, and then it will eat these things and produce, it'll produce various M files. One of them is called prog.m. So this is your main, by the way, you never even have to know or think or be aware of these kinds of things. But one of these things is called prog.m. That's the main MATLAB program. And these other two programs here are, one is the statement of the model equations, the actual dynamic equations in some kind of format that Dynare understands internally, always in MATLAB though. And the other one is the steady state equations, which is the same as this, but no time subscripts over here. And you may want to communicate inside here parameters that are living in the main program into here, and you use the parameter statement for that. If there's a parameter that only lives in here and does not need to be communicated down into any of these subprograms, you don't have to include it in the parameter statement. However, as a rule, you might as well just put in all parameters into the parameter statement. You never go wrong with that. You put in all constant terms here. Put in all constant terms. Just stick them here. Declaration of the deep. These are the deep parameters. I better get rid of the word deep there. That's not too good. So the time series variables are here, and the parameters are here. Now there's a third type of variable called var-exos. The var-exos are the exogenous shocks in the model. By exogenous shock, what I mean is the impulse to the exogenous shocks. So the actual shock itself, like U, which is the monetary policy shock, tau, which is the backache shock, these shocks, and the dA, which is the technology shock, these are actually variables. They're treated as endogenous variables in the model. And the exogenous variable is the impulse to that thing. So that impulse in the monetary policy shock is called epsilon U, epsilon A, epsilon tau. So these are the three types of variables which it can then use to interpret what's going on if you go down. We're in the model statement. So if we look inside this model thing, you can see in this first equation here, you got beta, and then you got a pi, and then notice I got a +1. What +1 means, well, if there were nothing there, then because Dynare now knows that this is a var, pi is a var, it's up in the var command. So if there's nothing there, then Dynare interprets that as a t. If there's a plus j in there, then Dynare interprets that as a t plus j. And here, notice x is a variable, but it has nothing in it, so that's xt. And pi is a variable, nothing in it, so that's pi t. Also, in terms of expectation operators, Dynare assumes that you have an ET in front of that, both sides of the equality. You have an ET on both sides. In the case of nonlinear equations, you actually want to think carefully about that, because that Dynare is also assuming that. You would never want to write an equation like here. Let's look at this, for example. Here's a first order condition. Beta times u prime ct plus 1 times RT. This defines the real interest rate R in, ET, but where RT is known at time t, this is a state non-contingent interest rate from t to t plus 1, that defines this thing here. So you could be tempted to write down an equation like this. You might be tempted in Dynare to write down R equals this, of course leaving out the ET, and then you'll be making a big mistake because Dynare runs the ET right through the whole thing. This is the right way to write it. You would write it this way. If you drop the ET operator, then Dynare will implement this. So you have to think a little bit about how you write the equations out to take into account the fact that Dynare is doing the ET operator in this way. Now, everything is linear here, so this is not the best framework in which to emphasize this. You'll see this when Jesus talks about this stuff tomorrow. Tomorrow, sorry. Okay, so here is the intertemporal equation. This is the real interest rate net of the natural rate of interest. This is tomorrow's gap. This is today's gap. This is just it should be a faithful and exact reproduction of the equations that we had in the handout. Here we have the monetary policy rule. Here you have rho R star is equal to rho A. Another way to write this would be simply this way, and forget the rho A stuff. That's actually the same thing. That's literally the same thing, what I just wrote, because, because et of da t plus 1, given the way dA is defined in the next equation, is the same as rho times dA. You know, you could run it both ways and see if you get exactly the same results. Actually, this is intuitively a little bit more, because R star is the growth rate is the prospective growth rate in consumption in the natural equilibrium, and if we were ignoring the tau for a second, that expected growth rate exactly coincides with the expected growth rate of A itself. So this is actually a little bit more, I don't know, we can write it the other way. It doesn't make any difference, but. Okay, so that's the natural rate of interest. This is the law of motion of that, There we go. That's the whole thing. And now I've defined the model. I've defined I assigned values to the parameters. I'm taking the special case where this is sort of like maybe, I don't know what, annual model or something. Anyway, beta is 0.99, not annual, quarterly. Phi x is 0, no weight on the gap. Phi pi is 1.5, alpha is no smoothing parameter, and so this is the exact example that we just did. And now, the other thing you have to do is you have to assign values to the var-exo guys. Var-exo guys are treated differently, different animals from parameters. They have their own personal type of syntax, and so you have to put in a shocks, and then this is an announcement that you're about to declare what the variance of epsilon A is, and then actually I'm declaring the standard deviation instead. I'm setting the standard deviation to 1, which is a ridiculous number, because that's 100% shock, but that's, because, right, these are all in logs, so 1 means 100%, but a more sensible number will be 0.01, but I multiply this by 100 so that the output can be thought of as having all been multiplied by 100. Everything's in percent terms. But then in the end, I'm not going to pay attention to any of those things anyway. So all these guys are set to 1. So far, all we've done is we haven't told it what to do. We've told it, basically, we've given it the model with the model command, and then backing up from there, we've differentiated which of the elements in the model are parameters, which are var-exos, which are variables, endogenous variables, and what are parameters. And then we set the parameters, we set the var-exo, so now we're ready to go someplace to do something with this thing. And the only thing that we're going to do here is to just simulate this model. And so what I've got is I've got the stochastic simulate command, which does the simulation, and what it does, and I've got a couple of things in there. One is I told it no graphs. So it produces all kinds of graphs, but they're not as beautiful as the graphs that you could write yourself, which we'll have right after here. So I always type in no graph. And then I got IRF equals 7 means that it's going to hit each variable with one standard deviation shock, which I set to be 1, and then it's going to supply supply 7 dynamic responses. Now there's a big question: where do you find those responses? And the answer is that the place where you find the responses is that what it does is it's going to compute the responses of all the variables in the var command. So suppose you had var, and one of the variables is x, which in fact it is. Then the place where you find the responses is you go to x. This will be in memory afterwards, after you execute this. You can think of this as being you could actually forget that this is a mod file. You can think of this as kind of being a MATLAB file, and that everything goes sequential, and then you're kind of thinking about it the right way. So the place where you're going to find this x thing is, this is the notation. You take the name of the variable as it appears in the var command, put an underline next to it, and then you write in the var-exo, the name of the shock that you want to get the response to. So we have, the names here are, say, epsilon A, EPS underline A. This, of course, you make up. This is also an underline. This you make up, but that you don't make up. That underline there signifies that you want the response of this endogenous variable to this var from this var-exo thing. And those are in memory available for you to access afterward. And in particular, the way I've written this thing, I've just started typing in MATLAB commands here. So I want to see what is the level of A. Well, these are growth rates of A, so to get the level of A, you have to calculate the cumulative sum of the A's. So this is just straight MATLAB here, just regular MATLAB. You can just type it right in. Think about the mod file as a sequential thing with some slightly weird language that you're not used to, like model and end, but then interspersed with MATLAB commands. And these commands will see the prog.m. When this thing writes this m file, you will find this code will be reproduced exactly in this form. Although you really have to have semicolons after everything, or it'll get totally screwed up. Because if you don't have the semicolon after figure, it will run into subplot, and that's not a MATLAB command. It's not any command at all. So you have to have semicolons. You know, you normally well, actually, I don't have a semicolon here, so I lied about that. Oh my God. Okay. So this is the whole thing. What? Yeah, I know. So now I'm confused. Sorry. So if we look inside this thing, you can see what I'm doing here. So here I'm plotting the cumulative sum of the response of to epsilon A. And then there's a title here that says level of technology, because I'm taking the cumulative sum of the changes in A, which translates into the level of A. And then here's inflation, and so you get a graph of that. Here you have the actual nominal interest rate. Here you have the natural rate of interest. Here is, well, so there's also hours worked here. And if you look at this, no, this is kind of a funny thing. Can anyone tell why this is a slightly weird thing here? What do you suppose the value of that is? How does tau respond to a technology shock? Well, it doesn't, because tau is an exogenous process that responds only. So that's nice to have it there, but that had better have just zeros in it. So notice what I've got here is I've got that the hours worked is equal to x. Does that make sense? If you look inside the model that we just derived, if you look inside there, you don't see any hours worked. How would we get hours worked out of the solution? Well, I'm saying let's look at the response of x. Why? Why is that? So if we look at the output gap, wait, where did I put the pen? There it is. If we look at the output gap, so we have xt is equal to yt minus yt star. That's the output gap. This, and let's suppose in response to A, in response to AT. So I look at it, yt, actual output, is equal to AT plus NT. And efficient output is equal to AT plus nothing. So where you get what x is in response to A, what x is, it's the response of n. That's how you read the response of n, and so that's why in that graph there I've got that. All right, what else we got going on here? Pi, r star, x is hours worked. Oh, here's actual output. This is a little bit trickier, actual output, because the y star is A, but we don't have A in the model, right? We have dA. We don't have A. So in order to recover actual output, what we've got to do here is, so what we have is x is y minus a. So I have to add a to it to get y. So that's what we got here. We're taking the output gap and add the level of a to the output gap to get the level of actual output. These are regular MATLAB commands, and so there they are. So why don't we, let's run this thing and see what happens. So we go over here, make sure in the right place, and there it is. And there we've got actually, it's better to have this thing over there. Let's just rewrite this so we can compare the actual and the natural rate of interest. So here's the here. This is extremely painful. TT equals 1 to length, R underline EPS underline A. And then let's graph the nominal rate and the natural rate. And we get this. Nominal rate, legend, actual nominal rate, and natural rate. So we go like this. Huh? Oh. Well, this is where the eating occurs. So you type Dynare space, you put the name of the file. Dynare assumes that you have a .mod at the end of that thing. It's not going to eat that, and it translated into MATLAB code. Well, let's look at the MATLAB. Although you don't actually have to look at the MATLAB code, but you might just feel really like you want to. So we'll do that. But to run this thing, I just type Dynare.space CGG, and then it just does a bunch of stuff. It runs it. The last instructions in there were this thing here, but we can look at some of the other stuff that it generated. So it has, it's giving out information about the, well, here it's giving out information. It's wonderful, actually, read this. So this is Michel Jouillard, has played a large role. He's as you can tell from the name, he's like a French guy. And if you look inside MATLAB, after you use Dynare by the way, Dynare is written almost entirely in MATLAB itself. There's a core part that no one is allowed to touch. It's secret, a stealth part, which is an executable file which you can't get into to see. But most of it's written in MATLAB, and it's got all kinds of notes written by Michel to himself in there. And half of them are in French, half of them are in English, and some words are half English and French all at once. We're not doing any econometric thing in here, but if you look at the econometric output, there's something when you do Bayesian thing called there's something called an acceptance rate. I don't know if probably everybody here is familiar with Bayesian stuff, but anyway, you do MC algorithm. There's something called an acceptance rate. And in his printout, it's the acceptation rate. And it's been that way since the beginning. I don't know. So anyway, he has all these little things. He just did his generalized QZ decomposition. He's just doing all these, giving you a little message. And he also gets very excited sometimes because he's like, we don't see that here, but you'll see exclamation points. I'm working on this, ... done! And all kinds of messages come to you as it's executing. See, look, processing. We didn't see that because it went too fast, but anyway, whatever. So that's just a bunch of information. Then he's got the number of things in the var command, 7 variables, 3 shocks. Those are var exos. What we call shocks actually aren't shocks. Money demand thing is not, the A is not a shock, or DA is not a shock, the var exos are shocks. Then he's got jumpers, people jumping off of buildings and things. It's wonderful here. And then you get some information on stuff. So it's calculating the variance covariance matrix of the shocks. And here what you have is the solution. That thing there is the solution. Remember, I defined before a solution as a matrix A and B. So you have this ZT equals A times ZT minus 1. Okay, so the ZT guys are up here. They're on they're the columns, dA, pi, r, and so on. And then the state onto which it feeds back is the rows. Now, Dynare is very efficient. The algorithm that I described this morning when I was quickly going through what a linearization algorithm does, I made the state the whole of the past ZT. That's very inefficient. You know, like if employment is a current variable, having lagged employment as a state variable is not efficient at all, because it's in fact not a state variable. And Dynare is extremely efficient and correctly calculates the state. So the number of rows is typically, I don't know what it is in this case, is less than the number of columns. But you can see here, look, that you can see this is a correct. In the case of you know what the correct policy rule is. Is 0.2 times minus 1 plus 1 times the innovation. And if it's not that, then you know it made a mistake. The other things you don't really know. I mean, that's what the solution has done. So you look at inflation. Inflation is a function of lag by that 0.07, lag tau, blah, 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 all these things. So that's the policy rule. That's the actual solution. That matrix, that's called GHX, it's a matrix called GHX, it's hiding deep inside the memory structure of Dynare, is something that can be recovered. Every calculation that Dynare does can be recovered somewhere in its memory. And it's pretty efficiently organized, so you can actually find stuff, although not totally. And they don't really have a serious manual for that. There is a manual, but it's not super, super good. So some hunting and pecking has to be done to find stuff. But every calculation, everything you ever do in Dynare is available someplace in memory for later use. We're not doing enough right now to really, impress you with that, because we're only doing a solution. So I can tell you can find that GHX. But if you're starting to do some you're starting to do Bayesian business and you're applying the smoother and all kinds of stuff, all the smooth variables, everything is planted somewhere and available for use. It's very good in that way. It's not great in the manual. I don't know why they haven't put more emphasis on that. It's okay. It has an okay manual, but it's not great. So here's the output gap. How does it depend? But notice here, this is a shock. This is what we would call an exogenous shock, and it only depends on its own lag and its own shock. So, and that's exactly the way it appears, and that's the way it has to be. Here we have it's calculating a second moment, mean and standard deviation and variance of the variables in the var, a command. And then we have a variance decomposition that's being reported. There's a bunch of information that's reported on the thing. That's what this output is about. And some correlations and stuff like that. Now and so on. But what I've been sort of, I think might be a good idea to focus on, I don't know why for sure, but is this kind of stuff here. And I thought what we could do is just play around with this stuff a little bit, and in the process do some economics, and in the process also get used to working with Dynare. So the first thing we see here, we just reproduce what's in the slides. Actually, you can reproduce exactly what's in the slides if you type in so the actual graph that I used is also available here. I think you will have noticed it in the zip file. There's a program called Plots, and so that's the one that actually produced, this stuff, all these little diagrams. But we don't need this fancy, this gorgeous graphics. Okay, so what I'd like to do is I'd like to go through just a list of things, and in the process, what you're going to discover is how easy it is to change a model, for example. We're going to just change the model, make some tweaks to the model, run the model again, and see what happens. So the first thing I suggest that we do is look at the sensitivity of the model to a change in the time series representation of A. So if we look at A here, the model of A that we have right now is this one here. With this model, what happens is when there's a shock, put time over here, put AT over here. If there's a unit shock to epsilon, that moves up A by 1 unit. And then A keeps on rolling in the same direction because it's autocorrelated in the first differences, and it asymptotes to 1 over 1 minus rho, because it jumps by 1, then rho squared, da-da-da-da, add them all up, you get 1 over 1 minus rho. That's the eventual impact of a shock to the level of A under that time series representation. And that's basically the whole story about the dynamic response. That's why you get this surge in demand, is that people see that their prospective situation is much better than the current situation, and that triggers this big increase in demand that exceeds even the rise in A itself. You see, the efficient thing is for demand to rise by exactly the rise in A, no more, no less, so that employment doesn't respond. That's the efficient thing in this economy. But what happens here is, at some level, the increase in demand is this whole amount here, right? If you keep the interest rate constant, they would just want to go to their new permanently sustainable level. It will be epsilon less, but not much. They would want to go all the way up to this thing, and the rise in the interest rate is designed to get them to do this. But the problem is that the Taylor rule, being too weak, doesn't raise the interest rate enough, so they actually increase their consumption by more. Okay, now let's try and change the story, and let's put this in here. So we have T, we have AT, and let's make it, instead of this, let's make it this. And so now, we've fundamentally changed the time series representation of A, because now when there's a shock to A, you're actually better off today than you will be in the future. Triggers exactly the opposite type of reactions to people, and let's see what happens. So we're going to have to change the program to do that. In the old days, when you had to program this stuff up yourself, this would be a nightmare. It would take you a whole afternoon. You'd be making 16 mistakes. Now we'll only make 1 or 2 mistakes, and we'll do it in a few minutes. So let's see. How do we do this? It's always true that R star has to be the expected growth rate of A. That's always true. It's always true that the efficient level of consumption is proportional to A. That's another weird thing about this model. The time series properties of A have nothing to do with what the efficient response in consumption is to A. It's always C is rising at the same rate, and employment is never supposed to respond. So for example, if you get news that tomorrow A is going to be a lot higher, you're supposed to work the same level today. Employment is always constant, and so C has to be going with A all the time. So let's, I don't know, why don't we, I mean, there's all kinds of things we could do here, but here I'll propose the most confusing possible thing. Let's just interpret dA as A, just to make sure that we all get confused. Okay, dA was delta A, now it's A. So what I want in here is plus 1 minus dA. Or, I mean, equivalently, it could be rho minus 1 times dA. Now, dA has to be interpreted as A. Actually, that's the only change we have to make. We don't have to change this equation because we just interpreted that as A. So that should be the whole ballgame. But notice what we've done here is we've changed the sign. We changed the sign on the response to a shock in this variable here from positive to negative, because rho is a negative number, which is exactly what we think should happen. That with a shock like the one on the bottom there, the natural rate of interest has to drop, because what's the problem is that is that people don't want to consume in response to this shock. There's going to be an inadequacy of aggregate demand. Actually, this shock is most people, if you go and talk to somebody on the street, you just go outside the front door here and you say, if there's a technological improvement, for example, we figure out some way that we can use, that 2 people can bake 100 loaves a day as opposed to 3 people. Most people would say, what would happen to employment? What would a normal person say if you tell them, look, it used to be with the old technology, you needed 3 people per oven. I got a whole new fancy oven, I only need 2 people per oven. What happens to employment? Down, right? That's what the normal person thinks. No? No? You guys never met a normal person, maybe. Normal people think that when there's a technological improvement that's labor-saving, you fire the bastards. Then when you tell them that, hey, there have been a lot of technical improvements since 1750, and all I see is a lot more people working, and then they get all confused. They say, that's history. I don't know what you're talking about. The normal person thinks that with a technological shock, but there's a way of translating it into economics. With a technology shock, an improvement shock, the normal person thinks that demand does not surge enough in response to that to soak up all the extra output that's necessary in order to keep employment unchanged. Well, this model of A is going to rationalize that view, together with the excessive weakness of the Taylor rule. So let's give it a shot here. Now, we got to change this figure a little bit. So, because now it's no longer true that you have to take the cum sum of so I don't know how we do this. One way we could do this. See, now you don't want to take to get A, you don't need the cum sum of A anymore. You need the, you just need A, DA. DA is now the level, so there's the level of technology. And then there was some other place where we had this happening. Where is it? No. Oh yeah, here. What is this? Oh yeah. Here's another place where we had to take the cumulative sum because dA was being interpreted as the change in A, but now it's the level of A. So there we go. So this should work and give us what happens. Boom, no mistakes. Okay, so let's see what happens now. All right, so if we look at the natural interest rate, if you look at the natural rate of interest, well, as expected, the natural rate of interest goes down. Why? Because there's inadequate aggregate demand. Nobody wants to spend. Why don't they want to spend? Well, because they want to save and they want to not spend today so they can spend more tomorrow or something. Because they're temporarily high. So the natural rate of interest drops. What happens with the Taylor rule? Too weak! You see? You see that? It's not cutting the interest rate enough. So what we have is, we have inadequate aggregate demand. Now, when I was a youngster, I was pointing this out at lunch. If anybody in the old days, like when I was your age, said the word inadequate aggregate demand, they were automatically recognized as a retarded human being. All you had to do was say, I think there's inadequate aggregate demand, you're retarded. But this model really and truly has in it the concept of inadequate aggregate demand, because in this simulation, the efficient thing is for the interest rate that there's something in the environment that makes people not want to spend. The efficient thing is to get the interest rate down so that they actually do that. The efficient thing is what's in the Ramsey equilibrium. How do we know it's efficient? Because it is. We computed the optimum. The optimum is the best. So that's the Ramsey. And but the Taylor rule doesn't move it enough. And so you're not getting enough stimulus to aggregate demand. As a consequence, look what happens to hours worked. It drops by 0.7%. And output, so it's not supposed to drop at all, but it does, so that's a regrettable thing. That fall in hours worked is bad. It's a bad thing. That's bad. And the output is rising, but it's not rising enough because look, it's incredibly how tragic this is. output should be rising by 1%, and it rises only by 1/4%. And this guy's, there's actually addition works here a little bit. So you can see hours worked is going by 3/4% going down, and output's going up by 0.75%. You add the two things up, and it's the one that it's supposed to be. That's the beauty of simple examples. See, this thing here should be, in the efficient equilibrium, goes all the way up to 1. Oh, look what happens to inflation. Look what's happening to inflation here. Because there's no demand, the firms aren't hiring anybody. Because they're not hiring anybody, the wage is going down. Because the wage is going down, marginal costs are lower, and inflation is dropping. So you can see here with the new Keynesian model, for example, the fundamental nature of the response of inflation, of hours worked, to a technology shock depends on what type of technology shock is it. Is it the one on the top of the picture, or is it the one on the bottom of the picture? By the way, if I had to put my bet on what technology actually is in the real United States of America, I would say it's the thing on the top. Technology isn't of the nature of you invent something and then you forget it, which is what the bottom is all about. Oh, I figured out how to make 10 loaves of bread with only one person, and then 3 weeks later, oh shit, I knew how to do it before, but now I forgot. See, that's not the way it works. So I would say that from that perspective, that in the context of the new Keynesian model, that technology shocks make inflation take off, and they make hours worked boom. Okay, so if we go, let's go here to look at some of these things. So, I need a little coordination strategy. So we're doing, okay, so what I'm going to do is I'll just continue. Let's just continue with this until the break, and then after the break, we'll go on to the financial frictions. Just do a couple more things here. Let me see if I can pick one. Okay. Well, why don't we just do the first two? We already did the third one. And, we already did the fourth one. And then, no, we won't do the bottom one. That one, but you could easily do it. You could just say, put in a shock that tells you that in the future A is going to go up, and then see how things respond. By the way, if you do that, what happens is, it's really quite amazing. You put in a future shock in here. It makes marginal cost go down in the future. These guys start cutting their prices today. But what does the Taylor rule do when you start cutting your prices today? Cuts the interest rate. What are you supposed to do? Well, when things look nice in the future, you're supposed to raise the interest rate. So it's going exactly the wrong direction. And there's some sense in which that may actually have something to do with historical data in the United States of America and in many other countries. What you observe is in the United States, over the last 200 years, in every single stock market boom that has occurred in the United States since 1807, inflation has been low during that boom. And so there is some idea that booms are associated with low inflation, and so if you're like a serious inflation targeter guy, that you're likely to respond by throwing fuel on that fire. If you think there's a boom underway which is a bubble or something, then because it's likely to have low inflation, after all, every boom in the United States, some of them must have been bubbles, has low inflation, you might think that. By the way, the poster child for this idea is Japan. So if you look at Japan, Japanese data, there's of course a famous boom, a stock market boom in the 80s. And the astonishing thing about the stock market boom in the 80s, I love it when I can draw data with my own hand because it's awkward. You know, when you have to draw the actual data, it doesn't always confirm with what you're, the story you're trying to tell. So if you put time here, and then you have the boom, the stock market boom. So this would be 1980 something, and you have the boom, and then you have 1990, something like that. So this is stock market. Then if you do the log of the price level, what's interesting about Japan is the log of the price level is rising at a decent clip up to the time of the boom. And then the minute the boom gets cooking, the price level flattens out. Indeed, the first kind of modern deflations that you see in Japan are in this period. And there erupted a debate inside the Bank of Japan at this time. You had, on the one hand, you had the people who were following the Taylor rule, which means you pay attention to inflation. They were saying, we got to cut the interest rate. Then you had other people who said, look, we got this crazy stock market boom underway. We got to raise the interest rate. Well, it turns out that the people who said you got to cut the interest rate won the debate. And if you look at the policy instrument of the Bank of Japan during this period, the rate's plunging. The nominal interest rate's plunging during this time. In fact, it's plunging not too far from what a Taylor rule would have told you to do. Not quite as much, actually. Taylor rule would have told you to do more. They didn't do it that much. But in any event, this is another example of how a stock market boom might very well, it seems to be often associated with low inflation. And this model kind of gives you an interpretation of that. Anyway, whatever. So we took care of this last one. So now we just have, let's see, potential. Oh, yeah, working cap. Okay, so the first two. So let me talk for a second here about, and this is kind of important partly for getting into the Dynare situation. So I want to talk about the Taylor principle for a minute. So the Taylor principle is that you set alpha pi bigger than 1. By the way, I'm going to need alpha x equal to 0, otherwise the details of the principle will change a little bit. So with alpha x equal to 0, then alpha pi bigger than 1 is somehow a nice thing. That is, if alpha pi is less than 1, you have the potential for self-fulfilling fluctuations. A potential for a form of instability that need not be present at all. And it's very trivial, the intuition, so I might as well just do that here. I can draw the model. It's basically ISLM model, so I'm going to do that. We have an IS curve here. Here's output. That's the nominal interest rate. But because this guy here is a function of the real interest rate, I'm going to need to have expected inflation here. And then we have Mr. LM over there. And then I'm going to have over here Y. And I'm going to have, this will be the Phillips curve, and this is actual inflation. So you might have some kind of I don't know what, you're in a situation that looks like that, okay? And what I mean by alpha pi being bigger than 1, what that means is that the monetary authority actually controls the location of that LM curve. So what the Taylor rule means is that they commit to moving the interest rate around, that is to say, moving the LM curve around, in such a way that the interest rate implied by the Taylor rule is satisfied. So let's suppose that this pi e goes up by some amount. The vertical shift, so people expect higher inflation. Let's not ask why. They're idiots. They saw a movie about Argentina, and they say, oh, Argentina. They speak Spanish in Argentina. They speak Spanish in New York. Must be we're going to get inflation in New York. Something. And so the expected inflation goes up by delta pi e, so this thing shifts up. And this vertical distance is exactly delta pi e because with this rise in the interest rate, the desired spending by people is unaffected because I'm assuming the IS curve, the people who are doing the spending in here are looking only at the real interest rate, okay? So what alpha pi bigger than 1 means is that these guys commit to shifting this LM curve back by more than this vertical distance. And let's see what happens if they do that. So we start out from this situation here. They raise the nominal interest rate by more than the rise in expected inflation. What does that do to the real interest rate? That makes it come down. And what happens when the real interest rate is coming down, in the model, probably not in the data, is that spending goes down. And where we end up with is over here. But what is happening to inflation? Actual inflation. It's coming down. The high real interest rate cut into demand, but demand drives output in the model, so output and employment go down, wages go down, blah, 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 and the actual inflation rate goes down, for the reasons we've already kind of gone through in our simulations. Okay, now, remember this was all triggered by people expecting higher inflation. Their expectations of higher inflation led them to anticipate higher inflation was going to occur, but it actually caused lower inflation to occur. What would happen to those crazy nuts who came out of the movie theater thinking there would be higher inflation when they see lower inflation? Well, they'll stop expecting higher inflation. Except the real lunatics who are completely committed to believing in higher inflation, but they will be ignored by people. So I'm giving you a learning interpretation of the Taylor principle. In rational expectations, this can't happen in the first place. No one would have this crazy expectation because they know it would only lead to the opposite from happening. In a learning environment, people could have this crazy expectation, but it would then be extinguished by what happens afterwards. And so this spontaneous increase in expectations that has nothing to do with anything would not occur. Or if it did occur, it could only survive a brief moment. In a rational expectations model, it can't happen. In a learning model, it could happen, but for a brief moment. Now let's suppose that alpha pi is less than 1. If alpha pi is less than 1, that means that when people expect higher inflation, they commit to raising the interest rate, because it's positive, but they raise the interest rate by less than this distance. So the LM curve ends up over here somewhere. You end up with higher output and higher inflation. So it could be that people started expecting inflation because they went to see a crazy movie and they got drunk afterwards and they had a stupid idea, but their expectations of higher inflation actually lead to actual higher inflation, in which case the origins of the belief become irrelevant because it's actually got higher inflation now. So this is an equilibrium. It's an equilibrium in a learning environment. It's an equilibrium. It's also rational expectations equilibrium. So in particular, we would expect, based on this logic, that alpha pi, so the Taylor rule logic, or the Taylor principle logic says, make sure your alpha pi is bigger than 1, because if it's less than 1, you're going to they're going to create instability in the economy. You'll create the possibility, you'll make the economy vulnerable to instability. These are fluctuations that have nothing to do with anything but people's expectations and are generally speaking not efficient in models. Not always. You can construct models where those things would be efficient, but generally speaking, those things are inefficient. So the case alpha pi less than 1 in technical terms is a case where there's multiple equilibria. And the case alpha pi bigger than 1 is the case where there's one equilibrium. We've already done alpha pi less than 1, bigger than 1. Let's try alpha pi less than 1 and see what happens in Dynare. And we can actually check the details of the logic here by making it just a teeny weeny bit. No, I know. Let's start out with this pi. I'm calling it alpha pi, but it's actually 5 pi. Let's make this equal to 1.0001. So the logic here would say we shouldn't notice any difference. Boom, everything worked fine, no problem. Thank you. Okay, now let's make it, now let's put it in 0.999. Let's go on the opposite side of 1. Blanchard-Kahn conditions are not satisfied, indeterminacy. Indeterminacy. Indeterminacy is a word for multiple equilibria. I'm sure many of you know, there are many concepts of multiplicity of equilibria, and indeterminacy is one type of multiplicity, and we have that consistent with this view. So the Taylor, and some people actually went on to argue, in fact, the guys Clare-Legali and Gertler went on to argue that this is the explanation for the high inflation of the 70s, that alpha pi was true. They went and estimated alpha pi, they find that it was less than 1 in the 70s, and then they said, aha, the high inflation in the 70s is what this theory predicts. By the way, did anybody see a flaw in what I just said? What does output look like during this high inflation? Huh? What does it look like? Is it green, pink? What does it look like? You probably want, now you know what does that question like that mean? What does output look like? Is it getting stronger or weaker? Huh? Yes, but what about in the model? Stronger. This is called the cross-equation restrictions. Even with multiplicity of equilibria, you have cross-variable restrictions. And this thing predicts that there should have been a boom in the 70s, but in fact, the 70s was the opposite of a boom. And so there's got to be something wrong with this exact story, at least the story about the 70s. Actually, I wrote a separate paper about this. I dickered around with a model a little bit, and I got it to work as a different model. But anyway, this is discussed at great length as another paper that, as far as I can tell, no one has ever read that paper. I've never met anyone who read I never met anybody who read this paper. So now there are even more people who have never read the paper than there were this morning. When okay. All right, so that's that. Now let's suppose we change the model one more time, and I think, oh, I lost my pen. And I think that the crisis makes us really think about this modification. So one of the things you notice is that firms, you discover in 2008, was how much people borrow on short term. And you never knew that. They borrow like for 4 days. They borrow for like 20 minutes. Actually, not 20. I made that one up. But they borrow for 4 days, 7 days, 14 days, really short-term borrowing. And if they can't have it, you hear gurgling sound coming from the firms, suggesting that it's like oxygen to them, borrowing short-term. That firms have a mismatch between the times when money comes in and the time that money goes out, like a university, for example. It gets money 4 times a year from tuition, and it's got to pay money out to people all the time. So it has a mismatch in terms of its inflows and outflows. And Northwestern uses short-term commercial paper markets to bridge those things. So let's just suppose, for the heck of it, that the firms borrow the whole of their inputs in markets. The whole wage bill gets borrowed. And in which case, the interest rate becomes a cost of doing business, just like the wages, but now the interest rate is. And so we have to then modify our little picture here, IS, LM, this thing. And in particular, this thing here, so output now, the inflation is going to be a function, is going to be shifted around for a given level of output. So the way this thing is set up right now is that higher output implies higher inflation. Why? Because higher output means you have to hire more people and they have to pay more wages. That goes into the price setting thing. So that's what the positive slope here is. But we could shift the whole curve up and down if we move the interest rate. So we think about the interest rate as being a shifter here. And now let's make alpha pi bigger than 1. So now, if we put in pi e, so now let's go through the same routine here. So there's a rise in expected inflation. So this thing here shifts up by the change in expected inflation. Alpha pi bigger than 1 means that they commit to shifting this thing out more, and which creates a recession. And if this curve here didn't change, then we would get lower inflation and blah, blah, blah. But suppose that the curve shifts, and it shifts a lot. Then the higher interest rate actually creates the higher inflation that they were afraid about. It's exactly the situation where you arrive at your house in the evening, it's burning, and you panic. Oh my God, my house is burning down. All my family photographs, everything is being burned. So you run and get a pail, you pour it full of liquidity, and then you throw it in the air, and you realize, what is that smell? Oh my God, that's gasoline I put in the bucket. Okay, that's what the high interest rate does if the working capital channel is sufficiently strong. So let's see how that works in this model. So how would we stick in that working capital channel? Well, just add the interest rate. And let's keep this to be a nice, healthy 1.5. And let's see what happens. So we run this thing, ta-dum. Indeterminacy. We now have exactly what that intuition suggests, which is that you have multiplicity of equilibria. So the Taylor rule, in particular the Taylor principle, if this working capital channel is sufficiently strong, then this Taylor principle actually is a bad idea. It's like throwing. In fact, by the way, normal people think this a lot. I don't know. Again, apparently you guys don't know normal people. But if you talk to, well, for example, I remember. So I had this job at I was working at the Minneapolis Fed a long time ago. And the president at that time was Gary Stern. And he was telling the board of directors, inflation is high. I'm going to go to Washington and raise the interest rate. There was this idea that somehow, once the Federal Reserve presidents arrive in Washington, they're all very meek and they're always bowing to his lordship, the chairman. But when they're back home, they're all, Anyway, so I'm going to go to Washington and I'm going to tell them to raise the interest rate. Anyway, so we had all kinds of people on the board. He was talking to the board, members of the board on the bank. And there was one guy with he had a very thick neck and thick finger. You couldn't even tell where his head and his body, they kind of fused. His job, he made concrete. That was his job. Because they get a representative. He said, look, Mr. Stern, I know you have a PhD from a very fancy university, and none of your sentences has words in it that are less than 3 syllables in them. Most of them I don't understand. I have to talk to people who've educated to tell me what the heck you're talking about. But I did hear you say that you're going to raise interest rates to get rid of inflation. And I remember him saying this. And what he says, I want to tell you, Mr. Stern, he raised his hand. You could hardly see the fingers because they were so fat. They're like mine. I have very fat fingers, but his were fatter, so it looked almost like a duck's thing. And he said, look, when you raise the interest rate, I don't know about all your fancy theories and stuff, but I'm raising my prices. I'm raising my prices because interest rates are a huge cost of my business. And so, I don't know what you can do whatever you say, whatever you like, but that's what's going to happen. Oh, by the way, a lot of people thought this way. In early 70s in Washington, we had one guy called Wright Patman, who was a very charismatic chairman of the House Banking Committee and who had a lot of power. Shouldn't go into all the details of that, but he had power over some critical legislation. And he, in those early days, people talked about raising interest rates to get rid of inflation. That was discussed in Washington. And he made it very clear to Arthur Burns at that time, who was the chairman, that Mr. Burns, he had a southern, accent. He's very charismatic, powerful character. And he said, Mr. Burns, you have all your fancy theories. I know you had something to do with Harvard and all kinds of other places, but I want to tell you something. You raise those interest rates, and that's going to make inflation worse. And what Wright Patman said was, I'm going to stop you from raising interest rates because I am Wright-Patman. I am in charge of the House Banking Committee, and I happen to be on the committee that's writing the wage and price control legislation. And if you make inflation worse, and what Wright-Patman said was, I'm going to stop you from raising interest rates because I am Wright-Patman. I am in charge of the House Banking Committee, and I happen to be on the committee that's writing the wage and price control legislation. And if you dare to raise the interest rates, I will take that interest rate and put it into the Wage and Price Control Board, and it will be decided there. You will not have control over the interest rate anymore, which is one of the most astounding events, I think, in U.S. monetary history, that one stroke of a pen and the interest rate control would have been taken entirely outside of the Fed. It was an amazingly lack of independence, at least in those early days. Okay, all right, so this idea of a working capital channel is kind of a thing. Now, I should add something about this working capital channel. In this model, it's actually not strong enough. We just put in the R and created indeterminacy, but that was a little bit unfair. If you were serious and you go into the model and you figure out exactly where does it belong, it's going to belong more like in kappa times R. It's going to have a kappa multiplying it. And in that case, you will not get this problem with the Taylor principle. Do you understand what I'm saying? In this model, if you put in a working capital channel, you make it really strong. Not here, I just put it in a reduced form way. I just went boom and I put it in. If you put it in as strong as you possibly can in a serious way in the model, you will find that it's not sufficiently strong to create this indeterminacy problem. However, it's my opinion that in this model, there's too little borrowing going on. This is a weird model. This standard model is weird in many ways, but in one way it's weird because gross output and actual output are the same thing. In this model, all production is headed towards the final consumption. The intermediate good producers are sending it up to the final good producers who are then sending it up to things. A more realistic version of this model is something that Susanto Basu has written about, where intermediate good producers are producing half of the stuff they produce is going to the final users, but half is going to other intermediate good producers. That's a more correct representation of production. So that the amount of kind of activity going on in the firms is a lot more than that what you actually see in just GDP. So I have a paper there's a handbook of monetary economics that just came out, I guess this year, that Woodford and Friedman did, and I have a chapter in there, and we go through a Basu type model, and we check to see could this working capital channel overturn the Taylor principle. And yes, indeed, when you have a Basu-style world where you're not just producing for final users, but also for other intermediate good producers, then you have the potential for much more borrowing and therefore a potential for a higher interest rate to shift that Phillips curve much more than you do in these very, very simple models. Okay.